Close your eyes and imagine the universe as it truly is. Not the bustling, chaotic place we often envision, but a serene, elegant tapestry woven from the fabric of space-time itself. Tonight, we'll drift through the gentle currents of Einstein's revolutionary ideas, letting the profound simplicity of relativity carry us into peaceful slumber. The story begins not with explosions or drama, but with the quiet contemplation of a young patent clerk in Bern, Switzerland, who gazed at the world around him and asked the most beautiful questions about the nature of reality itself. In the beginning there was light, not the blazing harsh light of midday, but the soft, constant whisper of electromagnetic radiation that permeates all of space. This light travels at a speed so fundamental to the universe that it serves as the cosmic speed limit, approximately 300,000 kilometers per second, or about 186,000 miles per second. Picture yourself floating in the vast emptiness of space, surrounded by this gentle sea of light. Whether you're moving toward a distant star or drifting away from it, the light from that star always reaches you at exactly the same speed. This seems almost impossibly serene in its constancy, like a cosmic lullaby that never changes its rhythm. Albert Einstein, in his contemplative moments, realized that this unchanging speed of light was not merely a curious property of electromagnetic radiation. It was a fundamental pillar upon which the entire structure of reality rests. No matter how fast you chase after a beam of light, you can never catch up to it. No matter how swiftly you flee from it, it always approaches you at the same unwavering pace. This constancy of light's speed is the first principle of special relativity, and it whispers to us about the deeper nature of time and space. Like a gentle stream that flows at the same rate, whether you walk beside it or ride alongside it in a boat, light maintains its eternal rhythm through the cosmos. Now let us gently explore one of the most beautiful and counterintuitive aspects of reality, the relativity of simultaneity. This concept suggests that there is no universal now, no single moment that exists simultaneously throughout the entire universe. Imagine two friends, Alice and Bob, floating peacefully in space. Alice drifts gently toward a distant star, while Bob remains at rest relative to that star. Between them, lightning strikes 2 points in space at what appears to be the same instant. Bob, positioned exactly midway between these two lightning strikes, sees them occur simultaneously. The light from both strikes reaches him at the same moment, confirming that they happened at the same time. But Alice, moving gently toward one of the lightning strikes, experiences something profoundly different. Because she is moving toward one flash and away from the other, she encounters the light from the approaching strike before the light from the receding one reaches her. From her perspective, the strikes did not occur simultaneously. One preceded the other. This is not an illusion or a trick of perception. Both Alice and Bob are experiencing reality correctly from their own frames of reference. The universe gently reminds us that simultaneity is relative, dependent on the observer's motion through space-time. Picture this like a soft symphony where different listeners, positioned at various points in a concert hall, might hear the same musical notes at slightly different times. The music remains beautiful and coherent, but the experience of when each note sounds depends on where you sit and how the sound waves reach your ears. Perhaps the most enchanting consequence of special relativity is time dilation, the gentle stretching of time that occurs when objects move at high speeds relative to one another. This phenomenon transforms our understanding of duration from something fixed and absolute into something fluid and relative. Imagine a peaceful journey through space at a significant fraction of the speed of light. As you glide serenely through the cosmos, something remarkable happens to time itself. While you experience the passage of time normally, your heartbeat remains steady, your thoughts flow at their usual pace. An observer watching from a stationary frame of reference would see your biological processes, your clocks, and even your thoughts slowing down. This is not science fiction, but a gentle reality of our universe. Time literally passes more slowly for objects in motion relative to a stationary observer. The faster you move through space, the slower you move through time. It's as if the universe has a cosmic conservation law. The total speed through space-time must always equal the speed of light. But you can redistribute that speed between motion through space and motion through time. Consider the famous thought experiment of the travelling twin. One twin embarks on a peaceful journey to a distant star at nearly the speed of light, while the other remains on Earth. During the journey, both twins experience time normally from their own perspectives. They age at the same rate they always have. Their clocks tick at the same familiar pace, and their daily routines unfold naturally. However, when the travelling twin returns to Earth, they discover something beautiful and strange. Less time has passed for them than for their earthbound sibling. The journey that felt like a few years to the traveller has been decades for the twin who remained at home. This is not merely theoretical, it's a measurable effect that has been confirmed countless times through experiments with atomic clocks and observations of fast-moving particles. Time dilation reveals itself in the most gentle ways throughout the universe. Particles called muons, created high in Earth's atmosphere by cosmic rays, have extraordinarily brief lifespans. Under normal circumstances, they would decay long before reaching Earth's surface. However, because they travel at speeds close to the speed of light, time dilation extends their subjective lifespans just enough for them to complete their journey to ground level, where we can detect them. Even the GPS satellites orbiting Earth must account for time dilation. These satellites travel at high speeds relative to Earth's surface, causing their onboard clocks to run slightly slower than clocks on the ground. Without correcting for this relativistic effect, GPS systems would quickly become inaccurate, accumulating errors of several miles per day. Just as time dilates with motion, space itself contracts in the direction of travel. This phenomenon, known as length contraction, represents another beautiful symmetry in Einstein's special relativity. While time stretches gently for moving objects, space compresses just as gracefully. Imagine a long, slender spacecraft drifting through the cosmos at a significant fraction of the speed of light. To the passengers aboard this vessel, everything appears normal. The corridor stretches the same familiar length from bow to stern, the viewing windows maintain their usual dimensions, and the distance between any 2 points within the ship remains constant. However, to an observer watching this spacecraft glide past from a stationary reference frame, the entire vessel appears contracted in the direction of its motion. The ship looks shorter, compressed along its length, while its width and height remain unchanged. This is not an optical illusion. The space itself has genuinely contracted. The mathematics of this contraction is elegantly simple. The faster an object moves, the more its length contracts in the direction of motion. At everyday speeds, this effect is imperceptibly small, but as velocities approach the speed of light, the contraction becomes more pronounced. At the speed of light itself, length would contract to zero, though no object with mass can actually reach this cosmic speed limit. This contraction of space is intimately connected to the dilation of time. Together, they represent two aspects of the same fundamental phenomenon, the geometry of space-time. Space and time are not separate entities, but are woven together into a unified fabric that responds to motion in these complementary ways. Consider a peaceful thought experiment. You're observing a train moving at relativistic speeds through a station. From your perspective on the platform, the train appears contracted, fitting easily within the station's length. But from the perspective of passengers on the train, it's the station that appears contracted, seemingly too short to contain their full-length train. Both perspectives are equally valid. Each observer experiences their own frame of reference as normal, while observing the other frame as contracted. This reciprocal nature of length contraction reflects the democratic principle of relativity. No reference frame is privileged above any other. Each observer's experience of reality is equally valid and equally real. The universe treats all uniformly moving observers with the same gentle impartiality. The most profound insight of special relativity is that space and time are not separate entities, but are unified into a single four-dimensional continuum called space-time. This union is not merely conceptual, it's a fundamental aspect of reality that reveals itself through the elegant mathematics of the Lorentz transformation. Imagine space-time as a vast four-dimensional ocean in which all events occur. Every point in this ocean is specified by four coordinates, 3 dimensions of space, length, width, height, and 1 dimension of time. Movement through this ocean is not arbitrary. It follows specific rules that preserve the cosmic speed limit and maintain the beautiful symmetries of relativity. When you move through space, you're actually rotating through space-time. The faster you move through the spatial dimensions, the slower you move through the time dimension. This rotation is analogous to turning a pencil in 3-dimensional space. As you rotate it, its projection onto different planes changes, but the pencil itself remains the same length. The mathematics of this rotation is governed by the Lorentz factor, a beautiful expression that depends on velocity. At low speeds, this factor is nearly equal to 1, meaning that relativistic effects are negligible. But as speeds approach the speed of light, the Lorentz factor grows larger, amplifying the effects of time dilation and length contraction. This four-dimensional perspective reveals why the speed of light is truly a universal constant. Light always travels at the same speed through space-time. Because photons move exclusively through the spatial dimensions, they don't move through time at all. From a photon's perspective, no time passes during its journey, no matter how far it travels. It experiences its entire existence as a single eternal moment. The space-time interval, which combines spatial and temporal distances in a specific mathematical way, remains constant for all observers. This interval is the four-dimensional equivalent of distance, and its invariance is what allows different observers to disagree about measurements of space and time while still describing the same physical reality. Consider the peaceful implications of this unified space-time. Every event in the universe, every moment of your life, every breath you take, every thought you think, occupies a specific location in this four-dimensional continuum. Your entire existence traces out a path through space-time called your world line, an elegant curve that represents your journey through the cosmos. One of the most famous equations in all of physics emerges from special relativity, E equal to mc2. This elegant relationship reveals a profound truth about the nature of matter and energy. They are not separate phenomena, but are different manifestations of the same underlying reality. The equation tells us that mass and energy are equivalent, related by the square of the speed of light. This means that even a small amount of mass contains an enormous amount of energy locked away in the very structure of matter itself. The speed of light squared is an incredibly large number, so even tiny amounts of mass correspond to vast quantities of energy. This equivalence is not merely theoretical. It's the source of the energy that powers the stars, including our own sun. In the sun's core, hydrogen nuclei fuse together to form helium, and in the process, a small amount of mass is converted directly into energy. This energy radiates outward, eventually reaching Earth as the gentle warmth and light that sustain all life. The process is remarkably efficient. The sun converts about 4 million tons of mass into energy every second, yet it has been shining steadily for billions of years and will continue to do so for billions more. This is the power of E equal to mc2. A tiny amount of mass provides an enormous amount of energy. Every atom in your body contains energy locked in its mass. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of these atoms are concentrated packets of energy held together by the fundamental forces of nature. In a very real sense, you are made of frozen energy, matter that has taken on form and structure. The equivalence of mass and energy also explains why nothing with mass can reach the speed of light. As an object accelerates, its kinetic energy increases, but according to relativity, this energy also contributes to the object's mass. The faster the object moves, the more massive it becomes, requiring ever greater amounts of energy to accelerate it further. At the speed of light, the energy required would be infinite, an impossibility that serves as the universe's gentle way of enforcing the cosmic speed limit. Photons, particles of light, have no mass, and therefore can travel at the speed of light. In fact, they must travel at this speed. They cannot slow down or speed up. They exist in a state of pure energy, moving eternally through the cosmos at the maximum possible velocity. 10 years after completing his special theory of relativity, Einstein embarked on an even more ambitious project, extending his insights to include gravity and acceleration. This quest led to the general theory of relativity, a breathtaking reconceptualization of gravity, not as a force but as a curvature of space-time itself. The journey began with a simple but profound observation. The experience of being accelerated is indistinguishable from the experience of being in a gravitational field. This insight, known as the equivalence principle, suggests that gravity and acceleration are two sides of the same coin. Imagine yourself in a windowless elevator. If the elevator accelerates upward, you feel pressed against the floor with a force that seems identical to gravity. If the elevator is instead stationary on Earth's surface, you experience the same sensation. Without looking outside, you cannot tell whether you're being accelerated upward or held stationary in a gravitational field. This equivalence led Einstein to a revolutionary conclusion. Gravity is not a force at all, but rather a manifestation of the curvature of space-time. Massive objects like stars and planets create curves and distortions in the fabric of space-time and what we perceive. As gravitational attraction is simply the natural tendency of objects to follow the straightest possible paths through this curved geometry. Picture space-time as a vast, flexible sheet. When you place a heavy ball in the center of the sheet, it creates a depression or curve around itself. If you then roll a smaller ball across the sheet, it will naturally curve toward the larger ball, following the contours of the warped sheet. This is analogous to how planets orbit the Sun. They follow the curves in space-time created by the Sun's mass. The mathematics of general relativity is expressed through Einstein's field equations, which relate the curvature of space-time to the distribution of matter and energy within it. These equations are remarkably elegant, describing how matter tells space-time how to curve and how curved space-time tells matter how to move. This curvature of space-time is not just a metaphor, it's a literal description of reality. Space and time are genuinely bent and distorted by the presence of mass and energy. The stronger the gravitational field, the more extreme the curvature becomes. General relativity reveals another beautiful aspect of time's flexible nature, gravitational time dilation. Time passes more slowly in stronger gravitational fields, a phenomenon that gently reminds us that time is not the universal, unchanging backdrop we once imagined. This effect arises naturally from the curvature of space-time. In regions where space-time is more severely curved, near massive objects like stars and planets, time flows more slowly relative to regions where space-time is flatter. The deeper you are in a gravitational well, the slower time passes for you compared to observers at higher gravitational potentials. Consider a peaceful thought experiment. Two identical clocks, one placed at sea level and another at the top of a tall mountain. The clock at sea level, deeper in Earth's gravitational field, runs slightly slower than the clock at the mountain's peak. This difference is extraordinarily small, only a few billionths of a second per day, but it's measurable with sufficiently precise instruments. The Global Positioning System provides a practical demonstration of gravitational time dilation. GPS satellites orbit Earth at an altitude where the gravitational field is weaker than at Earth's surface. As a result, clocks on these satellites run slightly faster than clocks on the ground. Without correcting for this effect, GPS systems would accumulate errors of about 38 microseconds per day, leading to positional inaccuracies of several miles. Near extremely massive objects, gravitational time dilation becomes more pronounced. Close to a black hole, time dilation can be dramatic. An astronaut falling toward a black hole would experience time normally, but to an outside observer, the astronaut would appear to slow down, their movements becoming increasingly sluggish as they approach the event horizon. At the event horizon itself, the point of no return around a black hole, time dilation becomes infinite from the perspective of a distant observer. The falling astronaut would appear to freeze at the horizon, their image redshifted into invisibility. Yet from the astronaut's perspective, they would experience normal time as they cross the horizon and continue their journey into the black hole's interior. This gravitational time dilation is not merely a curiosity of extreme environments, it affects us in subtle ways throughout our daily lives. Time passes slightly more slowly for your feet than for your head, because your feet are marginally closer to Earth's centre and therefore in a slightly stronger gravitational field. The difference is incredibly small, but it's real and measurable. One of the most striking predictions of general relativity is that light itself can be bent by gravity. This phenomenon, known as gravitational lensing, occurs because light follows the curvature of space-time just as matter does. From the perspective of special relativity, light always travels in straight lines through space. However, general relativity reveals that space itself can be curved, so light following a straight path through curved space-time will appear to bend when viewed from a distance. During a solar eclipse in 1919, Arthur Eddington conducted one of the most famous experiments in the history of science. He observed stars whose light passed close to the Sun during the eclipse, when the Sun's bright disk was blocked by the Moon. The stars appeared to be displaced from their usual positions, their light bent by the Sun's gravitational field exactly as Einstein had predicted. This bending of light has profound implications for our understanding of the universe. When light from distant galaxies passes near massive objects like galaxy clusters, it can be bent and focused, creating multiple images of the same galaxy or distorting its appearance into beautiful arcs and rings. These gravitational lenses act like cosmic magnifying glasses, allowing us to study objects that would otherwise be too faint or distant to observe. The bending of light also contributes to the phenomenon of gravitational redshift. As light climbs out of a gravitational well, it loses energy and its wavelength increases. shifting toward the red end of the spectrum. Conversely, light falling into a gravitational well gains energy and blue shifts. This effect has been measured in laboratories on Earth and observed in light from distant stars. Black holes represent the extreme case of light bending. The curvature of spacetime around a black hole is so severe that light paths can be bent into closed loops. There exists a region around a black hole called the photon sphere, where light can orbit the black hole in circular paths. Inside this region, all light paths eventually lead to the black hole's singularity. The bending of light also affects our perception of time and space near massive objects. Light signals take longer to travel between points in a gravitational field, an effect known as gravitational time delay. This delay has been measured in our own solar system by bouncing radar signals off planets and spacecraft when they pass behind the Sun. Among the most fascinating predictions of general relativity are black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. Black holes form when massive stars reach the end of their lives and collapse under their own gravity. If the star is sufficiently massive, no force in the universe can halt this collapse. The star's matter compresses into an infinitely dense point called a singularity, surrounded by a spherical region of spacetime so severely curved that it becomes disconnected from the rest of the universe. The event horizon is not a physical surface, but rather a mathematical boundary in spacetime. It marks the point of no return. Once you cross it, you cannot escape, no matter how fast you try to move or how powerful your rockets might be. The horizon exists because inside it, all paths through space-time lead inward toward the singularity. From the perspective of someone falling into a black hole, the journey across the event horizon is unremarkable. They experience no special sensation as they cross this boundary, and they continue to fall toward the singularity, experiencing normal time. However, tidal forces, the difference in gravitational pull between their head and feet, gradually stretch them in a process poetically called spaghettification. The view from outside is dramatically different. Due to gravitational time dilation, an external observer would see the falling person slow down as they approach the event horizon. The person's image would become increasingly redshifted, fading from view as their light is stretched to longer and longer wavelengths. They would appear to freeze at the horizon, never quite crossing it from the outside perspective. Black holes are not the cosmic vacuum cleaners they're often portrayed as in popular culture. They only capture objects that come very close to them or that are already gravitationally bound. If our Sun was somehow replaced by a black hole of equal mass, Earth would continue to orbit at the same distance, experiencing the same gravitational pull. The study of black holes has revealed profound connections between gravity, thermodynamics, and quantum mechanics. Black holes have temperature and entropy, and they slowly evaporate through a process called Hawking radiation. This evaporation is incredibly slow for stellar mass black holes. They would take longer than the age of the universe to evaporate completely. Near the event horizon, the extreme curvature of space-time creates exotic effects. Virtual particle pairs that normally annihilate each other can become separated, with one particle falling into the black hole while the other escapes. This process is the source of Hawking radiation and represents one of the most beautiful examples of how quantum mechanics and general relativity interact. Perhaps the most subtle prediction of general relativity is the existence of gravitational waves, ripples in the fabric of space-time itself that travel at the speed of light. These waves represent a completely new way of observing and understanding the universe, opening a window into cosmic events that are invisible to traditional telescopes. Gravitational waves are created when massive objects accelerate asymmetrically, causing distortions in space-time that propagate outward like ripples on a pond. The strongest sources of gravitational waves are among the most extreme events in the universe: the collision of black holes, the merger of neutron stars, and the final moments of massive stars as they collapse. The effect of a gravitational wave is extraordinarily subtle. As the wave passes through space, it alternately stretches and compresses distances in perpendicular directions. The amount of stretching and compressing is incredibly small. A gravitational wave from a black hole collision might change the distance between Earth and the Sun by less than the width of a proton. For decades, gravitational waves remained a theoretical prediction, too weak to detect with available technology. Einstein himself doubted whether they could ever be observed directly. However, in 2015, the Laser Interferometer Gravitational Wave Observatory LIGO achieved one of the most remarkable scientific breakthroughs in history by detecting gravitational waves from the collision of two black holes. This detection required instruments of unprecedented sensitivity. LIGO consists of two facilities, each containing laser interferometers with arms stretching 4 kilometers long. When a gravitational wave passes through the facility, it causes tiny changes in the length of these arms, which are detected by measuring the interference pattern of laser light. The first detected gravitational wave, designated GW 150,914, was created by the merger of two black holes approximately 3 billion years ago. The signal swept through Earth for about 0.2 seconds, during which the frequency of the gravitational wave increased from 35 to 250 sets. This chirp corresponds to the final moments of the black hole's spiral dance before they merged into a single, more massive black hole. The detection of gravitational waves has opened an entirely new field of astronomy. Unlike light, which can be absorbed or scattered by matter, gravitational waves pass through the universe largely unimpeded. They carry information about events that are completely invisible to traditional telescopes, such as the interiors of black holes and the moments immediately following the Big Bang. Gravitational waves also provide the most stringent tests of general relativity in the strong field regime. The properties of these waves, their frequency, amplitude, and polarization, match Einstein's predictions with remarkable precision, confirming the theory's validity under the most extreme conditions. General relativity not only describes the behavior of objects within space-time, but also reveals the dynamic nature of the universe itself. When Einstein first applied his field equations to the cosmos as a whole, he discovered that the universe could not be static. It must be either expanding or contracting. Initially, Einstein found this result so troubling that he modified his equations by adding a term called the cosmological constant, designed to allow for a static universe. However, in 1929, Edwin Hubble's observations revealed that distant galaxies are indeed moving away from us, with more distant galaxies receding faster than nearby ones. The universe is expanding, just as Einstein's original equations had predicted. This expansion is not galaxies moving through space away from us. It's the expansion of space itself. Imagine a balloon with dots painted on its surface. As you inflate the balloon, the dots move away from each other, but not because they're moving across the balloon's surface. Instead, the surface itself is expanding, carrying the dots along with it. The expansion of the universe means that in the past, everything was closer together. If we trace this expansion backward in time, we reach a point approximately 13.8 billion years ago, when all matter and energy in the universe was concentrated in an extremely hot, dense state. This moment marks the beginning of what we call the Big Bang, not an explosion in space, but the expansion of space itself. The rate of expansion is described by the Hubble constant, which relates the recession velocity of galaxies to their distance from us. Current measurements suggest that the universe is expanding at about 70 kilometers per second per megaparsec, meaning that for every million parsecs, about 3.26 million light-years of distance, galaxies are receding about 70 kilometers per second faster. The expansion of the universe has profound implications for our understanding of cosmic history. In the early universe, when everything was much closer together, temperatures and densities were extreme. As the universe expanded, it cooled, allowing the formation of the first atoms, stars, and galaxies. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old. Einstein's equations also predict that the expansion of the universe could follow different scenarios depending on the total amount of matter and energy it contains. If there's enough matter, gravity could eventually halt the expansion and cause the universe to collapse back on itself in a big crunch. If there's too little matter, the universe will expand forever, gradually cooling and diluting until it reaches a state of maximum entropy. Recent observations have revealed that the expansion of the universe is actually accelerating, driven by a mysterious component called dark energy. This discovery has added new complexity to our understanding of cosmic evolution and represents one of the greatest puzzles in modern cosmology. One of the most beautiful confirmations of general relativity and the Big Bang theory is the cosmic microwave background CMB, a faint glow of radiation that fills the entire universe and represents the afterglow of the Big Bang itself. In the early universe, temperatures were so high that atoms could not form. Instead, the universe was filled with a hot, dense plasma of protons, neutrons, and electrons. This plasma was opaque to light because photons would constantly scatter off the free electrons, unable to travel far before being absorbed and re-emitted. As the universe expanded and cooled, it eventually reached a temperature of about 3000 Kelvin, cool enough for electrons to combine with nuclei to form the first atoms. This moment, known as recombination, occurred approximately 380,000 years after the Big Bang. Suddenly, the universe became transparent to light, and photons could travel freely through space for the first time. These first free photons filled the universe with light, but due to the expansion of space, their wavelengths have been stretched over billions of years, from visible light into the microwave portion of the electromagnetic spectrum. This ancient light is the cosmic microwave background, and it provides us with a direct view of the universe as it existed when it was less than 400,000 years old. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who were working with a radio antenna at Bell Labs. They discovered a persistent background noise that seemed to come from all directions in the sky. Initially, they thought this noise was due to interference from pigeon droppings on their antenna, but further investigation revealed that they had discovered the afterglow of the Big Bang. The temperature of the CMB is remarkably uniform across the sky, with an average temperature of about 2.7 Kelvin, just a few degrees above absolute zero. However, sensitive measurements reveal tiny fluctuations in this temperature, variations of only a few millionths of a degree. These fluctuations are incredibly important because they represent the seeds of all cosmic structure. The slight variations in the CMB correspond to regions of the early universe that were slightly denser or less dense than average. Over billions of years, gravity amplified these tiny variations, causing denser regions to collapse and form the first stars and galaxies. The pattern of fluctuations in the CMB provides a detailed map of the conditions in the early universe and allows us to measure fundamental cosmological parameters with extraordinary precision. Observations of the CMB have confirmed many predictions of general relativity and the Big Bang theory. The spectrum of the radiation matches that of a perfect black body, exactly as predicted for the thermal radiation from the early universe. The polarization patterns in the CMB provide information about the physics of the early universe and may even contain evidence for cosmic inflation, a period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang. General relativity has revealed that the universe is far stranger and more mysterious than we ever imagined. Observations of galaxies, galaxy clusters and the cosmic expansion have uncovered two enigmatic components that together make up about 95% of the universe: dark matter and dark energy. Dark matter was first inferred from the rotation of galaxies. When astronomers measured how fast stars orbit within galaxies, they discovered something puzzling. The stars in the outer regions of galaxies were moving much faster than expected based on the gravitational pull of the visible matter alone. According to Newton's laws and Einstein's general relativity, these fast-moving stars should have been flung out of their galaxies long ago. The solution to this puzzle is the existence of dark matter, a form of matter that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. This mysterious substance interacts gravitationally with ordinary matter, providing the additional mass needed to hold galaxies together. Dark matter makes up approximately 27% of the universe, yet we still don't know what it's made of. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing studies show that massive galaxy clusters bend light from background objects more than can be explained by their visible matter alone. The cosmic microwave background radiation contains patterns that can only be explained if dark matter was present in the early universe. Computer simulations of cosmic structure formation require dark matter to reproduce the observed distribution of galaxies. Even more mysterious is dark energy, which makes up about 68% of the universe. This component was discovered through observations of distant supernovae, which revealed that the expansion of the universe is accelerating. This acceleration cannot be explained by ordinary matter or dark matter alone. It requires a new form of energy that permeates all of space. Dark energy behaves very differently from ordinary matter and energy. While matter and radiation become more dilute as the universe expands, dark energy maintains a constant density. As space expands, more dark energy appears to fill the newly created volume. This property gives dark energy a negative pressure, causing it to drive the accelerating expansion of the universe. The nature of dark energy remains one of the deepest mysteries in physics. It might be related to the cosmological constant that Einstein originally introduced and later called his greatest blunder. Alternatively, it could be a dynamic field that changes over time, or it might indicate that our understanding of gravity needs to be modified on cosmic scales. Together, dark matter and dark energy dominate the universe, relegating ordinary matter, the stuff of stars, planets and people, to just 5% of the cosmic inventory. This humbling realization reminds us that despite our sophisticated theories and observations, we still have much to learn about the fundamental nature of reality. General relativity opens fascinating possibilities for the nature of time and causality. While the theory doesn't explicitly forbid time travel, it reveals the deep connections between space, time and causality that make such phenomena extraordinarily unlikely in our universe. The concept of time travel in general relativity is closely related to the structure of space-time itself. In Einstein's theory, the past, present and future all exist simultaneously in the four-dimensional fabric of space-time. Your entire life, from birth to death, exists as a complete world line threading through this space-time continuum. From this perspective, the flow of time might be more of a subjective experience than a fundamental property of reality. One theoretical possibility for time travel involves closed time-like curves, paths through space-time that loop back on themselves, allowing an observer to return to their own past. Such curves could potentially exist in highly curved space-time, perhaps near rapidly rotating black holes or in exotic cosmic structures like traversable wormholes. However, the existence of closed time-like curves raises profound paradoxes. The most famous is the grandfather paradox. What happens if you travel back in time and prevent your own birth? Various solutions have been proposed, from the idea that the universe would somehow prevent such paradoxes from occurring to the notion that multiple timelines or parallel universes might exist. The study of these paradoxes has led to important insights about the nature of causality in general relativity. The theory preserves causal structure on a local level. Cause always precedes effect within any small region of space-time. However, the global causal structure can be more complex, particularly in the presence of extreme gravitational fields. Most physicists believe that some unknown principle, perhaps related to quantum mechanics, prevents the formation of closed time-like curves. This hypothetical principle, called the chronology protection conjecture, suggests that the laws of physics naturally prevent time travel paradoxes from occurring. Even without true time travel, general relativity reveals that time is far more flexible than our everyday experience suggests. We've seen how time dilation allows travellers to journey into the future by moving at high speeds or by spending time in strong gravitational fields. While these effects don't permit travel to the past, they do allow for a kind of one-way time travel to the future. The concept of simultaneity also becomes complex in general relativity. Events that are simultaneous for one observer may not be simultaneous for another observer in a different reference frame. This relativity of simultaneity means that the notion of a universal now breaks down, and different observers can disagree about the ordering of events. The relationship between general relativity and quantum mechanics represents one of the most profound challenges in modern physics. These two theories, each extraordinarily successful in their respective domains, seem to describe fundamentally different aspects of reality, and attempts to unify them have led to some of the most beautiful and complex ideas in theoretical physics. General relativity describes gravity as the curvature of space-time, treating space and time as smooth, continuous entities. Quantum mechanics, on the other hand, suggests that at the smallest scales, energy and matter come in discrete packets called quanta, and that uncertainty is a fundamental feature of reality. The first hint of the connection between these theories came from Stephen Hawking's work on black holes. Hawking showed that when quantum mechanics is applied near the event horizon of a black hole, the black hole should emit radiation and slowly evaporate. This Hawking radiation represents a profound connection between gravity, quantum mechanics, and thermodynamics. The process works through the creation of virtual particle pairs near the event horizon. Normally these pairs would annihilate each other almost instantly, but near a black hole, one particle can fall into the black hole while the other escapes. From the outside, it appears as if the black hole is emitting radiation, even though nothing can escape from inside the event horizon. This discovery revealed that black holes have temperature and entropy, with the entropy proportional to the area of the event horizon rather than the volume. This relationship suggests a deep connection between gravity and information theory, leading to insights about the fundamental nature of spacetime itself. The attempt to combine general relativity and quantum mechanics has led to theories of quantum gravity, which propose that spacetime itself might be quantized at the smallest scales, at distances approaching the Planck length, about 10 to the power of minus 35 meters. The smooth fabric of spacetime described by general relativity might give way to a foam-like structure where space and time become uncertain and discontinuous. String theory represents one of the most ambitious attempts to unify general relativity and quantum mechanics. In string theory, the fundamental building blocks of reality are not point particles but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles, including the graviton, the hypothetical particle that mediates gravitational interactions. Loop quantum gravity offers an alternative approach, suggesting that spacetime is made up of discrete units at the Planck scale. This theory proposes that space and time are not continuous, but are instead composed of tiny, indivisible loops that form a quantum foam at the smallest scales. The unification of general relativity and quantum mechanics remains one of the greatest challenges in physics. Such a theory would be essential for understanding the very early universe, the interior of black holes, and the ultimate fate of information that falls into black holes. It might also reveal new aspects of reality that we can barely imagine from our current perspective. General relativity, combined with quantum mechanics, has led to one of the most extraordinary ideas in cosmology, the possibility that our universe is just one of countless others in an infinite multiverse. This concept emerged from the theory of cosmic inflation, which attempts to explain the remarkable uniformity and flatness of our observable universe. Cosmic inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 10% to the power of 26 in less than 10% minus 32 seconds. During this brief period, a region smaller than a proton expanded to become larger than a basketball, smoothing out any initial irregularities and creating the uniform universe we observe today. The inflationary expansion was driven by a special type of energy field called an inflaton field. This field had the unusual property of maintaining constant energy density even as space expanded, providing the negative pressure needed to drive the accelerating expansion. Eventually, the inflaton field decayed, converting its energy into the hot, dense matter and radiation that filled the universe after inflation ended. One of the most remarkable predictions of inflation is that quantum fluctuations in the inflaton field during the inflationary period would be stretched to cosmic scales, creating the tiny variations in density that eventually grew to form galaxies and large-scale structures. These fluctuations are precisely what we observe in the cosmic microwave background radiation. However, inflation theory also suggests that the process might not have ended everywhere at the same time. While inflation ended in our region of space, allowing our universe to begin its more sedate expansion, inflation might have continued in other regions, creating an infinite number of separate universes, a multiverse. In this eternal inflation scenario, our observable universe is just one bubble in an infinite foam of universes, each with potentially different physical laws and constants. Some universes might be similar to ours, while others might be radically different, perhaps with different numbers of dimensions, different particles, or different fundamental forces. The multiverse idea raises profound questions about the nature of reality and our place within it. If there are infinitely many universes, then every possible configuration of matter and energy might exist somewhere. There could be universes where the laws of physics are slightly different, where the constants of nature have different values, or where the history of cosmic evolution followed a different path. Some versions of multiverse theory suggest that there might be universes where duplicates of you exist, living slightly different lives based on different quantum outcomes. In the vast expanse of the multiverse, every possible version of history might play out somewhere. The anthropic principle provides one way to think about our universe's place in the multiverse. This principle suggests that we observe our universe's properties not because they are inevitable, but because they are necessary for our existence. In a multiverse containing universes with all possible properties, we naturally find ourselves in one of the rare universes where conditions are suitable for life. One of the most puzzling aspects of our universe is the arrow of time. the fact that time seems to flow in only one direction, from past to future. This asymmetry is not built into the fundamental laws of physics, including general relativity, which are largely symmetric with respect to time reversal. Yet our experience of time is profoundly directional. The arrow of time is closely related to the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy tends to increase over time in isolated systems. This law provides a statistical arrow of time. While the fundamental laws of physics are time reversible, the probability of large-scale time reversal is vanishingly small. Consider a simple example. If you drop a glass and it shatters, the pieces don't spontaneously reassemble themselves. While the laws of physics don't prohibit such reassembly, the probability of all the glass fragments and sound waves reversing their motion to recreate the original glass is so incredibly small that it never happens in practice. The arrow of time manifests in many ways throughout the universe. Stars burn their nuclear fuel and eventually die, never spontaneously returning to their youthful state. The universe expands and cools, never contracting back to its original hot, dense state. Information can be lost or scrambled, but it rarely spontaneously reorganizes itself. The cosmological arrow of time is related to the expansion of the universe. As the universe expands, it cools and becomes less dense, providing a natural direction for time's flow. The cosmic microwave background radiation is cooling as the universe expands, providing a cosmic clock that measures the passage of time since the Big Bang. Black holes present interesting puzzles for the arrow of time. Information that falls into a black hole seems to be lost forever, violating the principle that information should be preserved in quantum mechanics. The resolution of this information paradox might require new insights into the nature of time, information, and the relationship between general relativity and quantum mechanics. The psychological arrow of time, our subjective experience of time's passage, is related to the increase of entropy in our brains and bodies. Our memories record the past but not the future, and our decision-making processes are oriented toward affecting future events. This psychological arrow aligns with the thermodynamic arrow, reinforcing our sense of time's direction. Some theories suggest that the arrow of time might be related to the initial conditions of the universe. If the universe began in a state of very low entropy, the natural tendency toward increasing entropy would provide a direction for time's flow. This low entropy beginning might be a consequence of the specific way our universe formed, or it might be a selection effect in a multiverse where only low entropy universes can support observers. General relativity not only describes the evolution of the universe from the Big Bang to the present, but also allows us to peer into the cosmos's distant future. The ultimate fate of the universe depends on the balance between the expansive force of dark energy and the attractive force of gravity, along with the fundamental properties of space, time, and matter. Current observations suggest that dark energy dominates the universe's energy budget, driving an accelerating expansion that will continue indefinitely. In this scenario, known as the Big Rip or heat death, the universe will expand forever, becoming increasingly cold and dilute as time progresses. In the far future, star formation will gradually cease as the universe runs out of gas to fuel new stars. Existing stars will burn through their nuclear fuel and die, leaving behind white dwarfs, neutron stars, and black holes. The universe will enter a dark age, lit only by the occasional flares of matter falling into black holes and the rare collisions of dead stellar remnants. Even the most stable structures will eventually succumb to the passage of time. Protons, the building blocks of atomic nuclei, might decay after incredibly long periods, perhaps 10 to the power of 34 years or more. If protons do decay, then all matter as we know it will eventually disintegrate, leaving only a sea of elementary particles and radiation. Black holes, which seem so permanent and inescapable, will also eventually evaporate through Hawking radiation. The larger the black hole, the slower it evaporates, so stellar mass black holes will persist for about 10 to the power of 67 years, while supermassive black holes might survive for 10 to the power of 100 years or longer. But even these giants will eventually fade away, leaving only a faint whisper of radiation in the vast emptiness of space. In the ultimate future, the universe might reach a state of maximum entropy, where all energy has been evenly distributed and no more work can be done. This heat death represents the end of all structure and complexity, with the universe existing as a thin soup of elementary particles and radiation at a temperature just above absolute zero. However, some theories suggest alternative fates for the universe. If dark energy is not truly constant, but instead varies over time, the expansion might slow down or even reverse. A big crunch scenario would see the universe collapse back on itself, with galaxies, stars, and eventually atoms crushed together in a mirror image of the Big Bang. Another possibility is the Big Rip, where dark energy becomes so dominant that it overcomes all other forces, tearing apart galaxies, stars, atoms, and eventually even space-time itself. In this scenario, the universe would literally rip itself apart in a finite time, perhaps 20 billion years from now. Some versions of string theory and quantum gravity suggest that the universe might be cyclical, with periods of expansion and contraction repeating indefinitely. In such models, our Big Bang might be just one event in an eternal cycle of cosmic rebirth and destruction. The vast timescales involved in these cosmic scenarios are almost incomprehensible. The current age of the universe, 13.8 billion years, is infinitesimally small compared to the eons that lie ahead. Civilizations might rise and fall, stars might be born and die, and entire galaxies might evolve and disperse, all within the briefest moment of cosmic time. As we reach the end of our journey through the theory of relativity, we find ourselves in a universe far stranger and more beautiful than our everyday experience suggests. Space and time are not the fixed stage upon which events unfold, but are dynamic, flexible entities that respond to the presence of matter and energy. The familiar concepts of past, present, and future give way to a more complex understanding of temporal reality. Einstein's insights have revealed that we live in a universe where time can slow down or speed up, where space can curve and bend, where matter and energy are interchangeable, and where the very fabric of reality ripples with gravitational waves. These discoveries have not only revolutionized our understanding of the cosmos, but have also provided practical technologies that affect our daily lives. The global positioning system relies on corrections for both special and general relativistic effects. Particle accelerators must account for the increase in mass, with velocity predicted by special relativity. Medical imaging techniques like PET scans depend on the annihilation of matter and antimatter, converting mass to energy according to E equal to mc2. Yet perhaps the most profound impact of relativity is not technological but philosophical. Einstein's theories have taught us that the universe is far more interconnected than we previously imagined. Space and time are unified, matter and energy are equivalent, and the seemingly separate phenomena of gravity and acceleration are different aspects of the same geometric reality. The universe revealed by relativity is one of elegant mathematical beauty, where the most complex phenomena emerge from simple, fundamental principles. The curvature of space-time, the constancy of the speed of light, and the equivalence of mass and energy combine to create a cosmos of extraordinary richness and complexity. As you drift into sleep, let the gentle rhythms of the universe carry you forward through the dimensions of space-time. You are part of this cosmic dance, a temporary arrangement of matter and energy that has achieved consciousness and contemplated its own existence. The same fundamental forces that govern the motion of planets and the collision of galaxies also govern the beating of your heart and the firing of neurons in your brain. In the quiet moments before sleep, remember that you are made of star stuff, forged in the nuclear furnaces of ancient suns and scattered across the cosmos by supernovae explosions. You are connected to every other part of the universe through the fabric of space-time, participating in the eternal dance of matter and energy that began with the Big Bang and will continue long after the last star has died. The theory of relativity is not just a scientific theory, but a profound meditation on the nature of existence itself. It reminds us that reality is far more subtle and interconnected than our senses suggest, and that the universe is filled with wonders that we are only beginning to understand. Rest now in the knowledge that you are part of something vast and beautiful, a universe where space and time dance together in perfect harmony, where matter and energy transform into one another in an endless cycle, and where the deepest mysteries of existence await our continued exploration and wonder. Sweet dreams, fellow traveller through space-time. May your journey through the dimensions of sleep be as peaceful and profound as the cosmic journey we have shared together through the elegant landscape of Einstein's relativity.